Hello, my name is Alessandro, and welcome to another Tech Talk in our series sponsored by CodeSmith, Genie, and Bracklad. Today, we have the pleasure of having Mark Krasner talking about message brokers. So with that, I'll pass it over to you, Mark.
Thank you so much for the warm introduction. I'm Mark Krasner, and I'm excited to talk with you all today about message brokers. But before we get started, I would like to thank CodeSmith, Genie, and Bracklad for sponsoring this Tech Talk. As I just mentioned, the topic we'll be covering today is message brokers. More specifically, I'm hoping to double-click into the many reasons why engineering teams building complex systems today choose message brokers over other available options. To help us understand these reasons, we'll need to define what they are and what problems they set out to solve. It's also important to understand which use cases they would not be ideal for based on their underlying mechanics. By outlining these features, I hope to leave you with a better idea of how you can start using message brokers to address your engineering challenges. To set the stage, we'll first start by defining what message brokers are and how they work. Next, I'll walk through two of the most common message broker models, which will be helpful to understand given how these paradigms have shaped some of the most popular message broker platforms in use today. I'll also point out the main reasons why you might want to use a message broker, as well as ideal use cases. Finally, I'll cover the differentiating factors between message brokers and other adjacent options, as well as some of the most popular frameworks in use. So what is a message broker? Simply put, a message broker is software that enables systems, services, and applications to communicate with each other. Furthermore, message brokers allow interdependent services to interface with each other directly, even if those services are written in other languages or exist on separate platforms. As TIBCO points out, the defining characteristic of a message broker is that the broker itself is a discrete service, while allowing enough flexibility that enables producers and consumers to communicate with the broker using standard or proprietary protocols. Message brokers also typically take care of state management and client tracking internally. This is powerful because it takes that burden off of individual applications or services that otherwise might need to worry about this responsibility. To help further define what message brokers are, we need to understand a bit about their basic infrastructure. To begin, message brokers will generally always have producers and consumers. Producers are responsible for sending data to be distributed by the message broker, while consumers either request or subscribe to certain message groups based on broker partition logic. At the core of this infrastructure lies a data structure that holds the messages in a particular order prior to routing. Most platforms employ a first in, first out data flow, or a queue. However, it's important to note that some platforms, like Kafka, persist data by using a log, meaning that the message remains in queue even after it's been consumed. Finally, while the terminology differs across platforms, most brokers also employ an exchanger responsible for creating message groups to which producers and consumers can write to or listen in on. Now that we understand a bit about basic broker infrastructure, let's talk about how message brokers work. While later in my talk, I'll cover how different message types and different broker model types lend to different functionalities and features, I'll take this opportunity to take a step back and talk about asynchronicity. One of the reasons message brokers are so useful in the right context is that they promote asynchronous communication among services. Rather than a source app submitting a message to a target, waiting for it to process, and requiring a response to continue, known as a blocking request, message brokers don't require real-time responses. This asynchronous behavior is preferential because it improves fault tolerance and resiliency, making it easier to scale systems. Something I personally find fascinating about different message broker systems is how their underlying models differ, resulting in some use cases being better suited than others, given the broker model. While hybrid models are used in certain platforms, there are two predominant distribution models. Commonly referred to as pub/sub, the publisher subscribe distribution pattern also allows subscribers or consumers to indicate that they would like to receive messages from a particular message group called a topic. Message producers then publish data to those topics, which are automatically received by subscribers. A good analogy here would be an airline broadcasting updates about data related to its flights, with ground crews, baggage handlers, pilots, and consumers consuming only the data that's relevant to them. Conversely, point-to-point describes a message queue where the sender and receiver have a one-to-one relationship. Each message is sent to and consumed by only one recipient. Think of an employer paying a contractor a lump sum for a service. In this situation, each party wants assurance that the payment will be sent once. Given these core features and models, what would be the main motivations to use message brokers? To start, perhaps the most obvious motivation would be to decouple a system's architecture, making it more resilient and fault tolerant. Since producers don't need to know about downstream consumers, this allows data producing services to focus their energy on providing their core functionality. In a distributed system setting, parallel processing is a huge motivating factor, allowing multiple downstream processes the ability to be notified when events occur. Third, message brokers can be used to reduce back pressure from downstream services, potentially preventing them from getting overloaded, which also improves resiliency. Finally, many brokers provide retry event functionality or data persistence to prevent any information from being lost. Given these benefits, what settings and systems would be best suited for message brokers? While there are many to discuss, given our time, I'll focus on two of the most compelling use cases. First, message brokers are extremely powerful in the context of microservices, specifically in the realm of addressing the challenges of coordinating communication between discrete services. While a simple REST API might initially serve this purpose, integrating an event-based architecture using the pub/sub pattern would be far more fault tolerant. My personal favorite use case is in transactional systems. Consider a platform like YouTube that relies on various services to validate, compress, and modify an uploaded video before publishing. A message broker is a great fit to coordinate data flow dependencies while also defining logic around which services can run in parallel. It's also helpful to understand how message brokers differ from other communication paradigms. For example, REST APIs use the Hypertext Transfer Protocol, or HTTP, to communicate, which is inherently a request-response model. Therefore, REST APIs are best suited for situations that require an immediate response, while message brokers allow data to flow asynchronously. Event streaming platforms differ from message brokers such that they are strictly defined to using a pub/sub style distribution model, while message brokers support point-to-point and even hybrid models. While they share many similarities, message brokers are also more lightweight than an enterprise service bus and are often less challenging to integrate and less expensive to maintain. While the total list of message broker platforms extends far beyond what you see here on this page, these are some popular options. To bring some of these concepts full circle, you might recall how I mentioned that some message broker platforms differ in what data structure they use to organize messages. Apache Kafka, for example, is one of the platforms that appends messages to a log and leaves them there until the consumer reads it or until it reaches its retention limit. RabbitMQ, on the other hand, uses queue-based architecture, hence the MQ or message queue. Kafka appears on the surface to use a pub/sub topology, though under the hood, it uses long polling, while RabbitMQ is more general purpose and uses variations of point-to-point and pub/sub communication patterns. While we don't have time to talk about each in detail, I'd like to point out how predominant message brokers are across many of the brands and products we engage with on a daily basis. Take Kafka, for example, which is used by over 80% of Fortune 100 companies, including the New York Times, Fox, Netflix, and Salesforce. Message broker technology also continues to be dynamic and innovative. with newer platforms like Apache Pulsar setting out to address a different set of challenges by offering cloud-native infrastructure, offering impressive performance numbers such as fewer than 5 millisecond deployment response times. While in Kafka, brokers must synchronize data with other brokers and their replicas on the same partition, Pulsar completely separates state from the data storage layer. While Kafka clients must interface with Kafka brokers to consume and produce messages, requiring the broker to store events as needed, Pulsar uses stateless proxies as brokers. I know that was a lot of content to get through, so I'd like to circle back and review some high-level points I hope to leave you with. First, message brokers use one of two predominant message models that defines how clients engage with them, the publisher-subscribe model and point-to-point. Message brokers offer powerful benefits given that they're asynchronous, can handle high throughput, and enable parallel processing. When configured correctly, they can be extremely effective in the context of distributed system design, microservices, and transactional systems. Finally, Apache Kafka, RabbitMQ, and IBM MQ represent three of the more well-known platforms in the space. Unfortunately, it seems that we've run out of time for questions, but please reference my works cited if you'd like to learn more. You can also send me a message on LinkedIn if you'd like to talk more about message brokers, and feel free to explore what my team and I have been building at Xkite to make it easier to configure, test, monitor, and use Kafka. Thanks so much for joining me today, and I'd like to now pass it back to Alessandro.
Thank you for that wonderful talk, Mark, and thank you for everyone for coming. See you next time.